Welcome everyone to another episode of the Hidden Quantum Champions. In today's video we have another company from the space of quantum computing and quantum technology, and let's jump right into it. Today we are looking at Horizon Quantum. So here I'm on their website. You see ones and zeros that are turning into waves, which is symbolic for what the quantum computer is doing. I like this little graphical background game here. And looking at the website, it says, harness the power of quantum computing, explore our developer tools that simplify the process of programming quantum computers, discover our technology. So that's the call to action. We will not follow that one, but from that we can already see here we are in the software space, right? So this is about like the uppermost layer, making the quantum computer actually accessible. So let's see what their approach is. Here it says, and I like the graphics that they have, like the graphical works that go along on the website, which are symbolic probably for what it says in the text. So our approach to quantum programming. We believe that programming quantum computers should be as straightforward as programming conventional computers. To this end, we are developing tools that automatically accelerate code initially written from conventional systems for efficient execution on quantum hardware. Our commitment is to build tools that fully harness the power of expressiveness of quantum computing, ensuring it is as accessible and functional as traditional computing. So, as far as I understand, it basically takes an existing program like in C++, it identifies maybe the sections in the code or the algorithms that are being used in the code to solve specific issues, like, I don't know, traveling salesman problem, and then maps them onto a quantum computer. But let's move on the website and see what it tells us. So, abstract away the complexity of quantum physics and enable domain experts to harness the power of quantum computing. Today, equip yourself with tools to program quantum computers in a language that offers a simple basic-like syntax with advanced capabilities, including concurrent classical and quantum computation and control flow that takes you beyond circuits. Tomorrow, empower developers, regardless of their level of quantum expertise, to benefit from the potential of quantum computers by harnessing quantum algorithm synthesis to automatically accelerating programs written in classical languages. Here we see Triple Alpha, which is available apparently in early access. I guess this is the software platform. Here it says Triple Alpha is our web-based integrated development environment, IDE, which allows you to easily write complex software for quantum computers. Code at different levels of abstraction according to your workflow, compile to target specific quantum processors, quantify resource requirements, and deploy programs as APIs to run when needed. What we see here is the code, which looks a little bit like a Pythonic type of syntax. But I guess there's also something like C in here, so maybe there are also different languages available, and I guess we will learn about that down the line. Also probably which different platforms you can actually use. So, core capabilities. Explore capabilities that redefine the boundaries of what's possible in quantum computing and make Triple Alpha the only choice for serious quantum software development. It says, touring complete languages, leverage control flow to overcome the limitations of circuit-based quantum computation. Then subroutines from C and C++ automatically construct reusable quantum circuits directly from functions written in C and C++. I guess this is what I was referring to earlier, actually by coincidence even in exactly this language. And then code portability, compile and optimize quantum programs and map them to the native operations of any target hardware. Here again, open bracket, right? So there are different types of platforms out there. There's, for example, ion-based quantum computers, and there are superconducting ones. And they are working basically fundamentally in a different way, right? So one is using ions and different level systems in the ions to encode the quantum information. The other one is using, let's say, the bosonic, well, no, not bosonic, but like the properties, the quantum properties of superconductors and Josephson junctions, so macroscopic systems, in order to encode quantum information. For example, in the phase, if you have like, depends on what type of qubit you have. But now, these systems come with different properties, different advantages and disadvantages, as for example, the execution speed at which they can operate, the coherence time, so how long can actually the quantum information be contained until it decoheres, until it gets lost and the system basically just enters a random state. So if you can operate fast, you might not need a super long coherence time, but if you can operate only very slow, you require a long coherence time, right? Now, there's also terms of scalability, right? Some computers can have hundreds of qubits, other ones are a little bit more limited right now. But then there's also the precision at which the execution can happen. So how sure are you actually, if you flip your qubit from 1 to, let's say, a superposition state, that it's really like in a 50-50 superposition, for example? What is the influence of the externals, right? So how is and that then eventually plays into the decoherence. So all of these things, and on top of that comes the topography of the system. So for example, we looked at different companies from the superconducting space previously. And when you have a superconducting qubit, you usually have some couplers which you can use to couple this qubit to another one. There are cases where the qubits are just lined up in like what looks like a one-dimensional chain. So you can only couple one qubit to the other one if they're neighboring each other. There are other ones that have like maybe a star shape where you can couple a center qubit to every single one of them. And that also has some implications on how you can actually encode your code, or how you can map your code on the existing quantum system, on the existing quantum hardware. And this is what this compilation and optimization here probably does, or what I would assume it does. Close bracket, back to the website. So get started. There are various ways to engage with us, whether you're interested in technology, looking to use our tools, or simply curious about what we do. So there's the explore stage, venture into quantum programming with our technology. So there's triple alpha. Then learn, delve into our resources and opportunities for collaboration. There's a blog and an early access program here. And the discover stage, stay up to date with our latest news and events. So there's company news. So there's about the company news, and then there's also the events where they probably exhibit something, like conferences, trade shows, whatever. Triple Alpha and Early Access. If you are interested in early access to our technology, please register below. We will be inviting selected users to early access based on use cases as we progressively release our tool. Note or call to action for everyone. If you want me to test this, please write it down in the comments below. Then I will register here, and let's see if I can do then a little tutorial or a little walk through the software in the early access for you guys. As always, let's quickly hop through the different sections of the website and see what else they offer here in terms of information, and then we will end up with, as always, a little look at the company profile, how they describe themselves in this tab. Okay, let's start with the mission. We see a mountain here with the way up, so the journey to a quantum world. At Horizon Quantum, we believe quantum computing has the potential to spark a second revolution in computing. Our mission is clear: to enable a world powered by quantum computation. And I do agree in a way with the statement here. I think as well that if we manage to get quantum computers up and running, this will accelerate a lot of things, and we will be able to solve problems that right now seem unsolvable for us. And if we have a computer that uses the mechanics that are behind how nature works, and right now quantum theory is our most accurate description of how nature works by all measurements that have been done so far. So if this theory is correct, or at least if it's correct to a certain number, And we can actually make use of this to compute things, then like simulation of materials, understanding how the materials actually work. All of this will become possible with quantum computers. And all of these applications that we are always seeing, like pharmaceuticals, material development, and so on, they will suddenly become possible. And on top of that, there are also some mathematical problems that, let's say, not necessarily one-on-one map with something that we are seeing in material research, but that are more like mathematical problems. They will also become feasible. Part of that is like the whole story about AI and finance-related things and network optimization and so on. Close bracket, we move on with what is written here on the website. Advancing hardware alone will not unlock the full potential of quantum computers. We must also empower users to harness their power to tackle real-world problems. This necessity defines what we call the application bottleneck, a challenge we are dedicated to overcoming. And indeed, I also feel like if this is really going to take off, there will be an application bottleneck. From my point of view, that starts already a little bit further up. So we need to get leaders of organizations, and organizations can be companies, like private organizations, can also be states, as in, okay, we need to understand our strategy on cryptography and things like that. The leaders need to understand it first, from my point of view, and then we need to get, let's say, some movement into the organizations. And for some things, like for example for cryptography, it might already make sense to look into this today. Close bracket, we move on. Sorry for all the notes in between today. I don't know. I feel like I need to add a little bit more context because people are also asking me for that. So the application bottleneck, getting quantum computers to do useful work is challenging. Why is that? Because there's a limited talent pool. Developing meaningful quantum algorithms requires deep expertise. However, the number of researchers with the required skill set is very small. These are these famous PhDs that everyone's always talking about, quantum information theorists. Non-intuitive process. Quantum mechanics defies our intuition, making it difficult to construct meaningful algorithms. And then primitive tools. Quantum programming tools are still severely limited, requiring gate-by-gate construction of programs or necessitating reliance on pre-built libraries. So this is like basically, I don't know. I haven't gone through the times of assembly, but I imagine that like right now what is being done is you really have to basically tell the quantum computer which qubit to flip or how to entangle them and so on. And to me that feels like a little bit like the old assembler times in computers, where you really had to tell the computer which gates to actually perform like the lowest level of programming language. And yeah, maybe there's some parallel here. But on top of that, there are also libraries, probably by Horizon Quantum and also other solution providers, right? So we are pursuing an ambitious plan to make programming quantum computers as easy as programming conventional ones. So there's the solution to the limited pool access here, quantum programming for every software developer. We are building the most capable and easy to use tool to enable you to write complex programs for quantum hardware. Quantum programming should be accessible to every software developer, not just quantum experts. Then non-intuitive process, unified computing. At the core of our approach is the compiler that accelerates classical programs by detecting opportunities for quantum advantage and automatically generating corresponding quantum algorithms, enabling interoperable code for both classical and quantum systems. And then the final one, primitive tools, power through abstraction. Our tools are designed to empower developers to engage with quantum computing at their preferred level of abstraction, whether they are harnessing automated algorithm synthesis, crafting custom quantum algorithms, or exploring physics with processor-specific code. A team pushing the frontiers of quantum technology. We are deeply committed to propelling quantum computing into the next era as a passionate and ambitious team, united by a shared vision, we are determined to overcome challenges and realize the full potential of this transformative technology. On this journey, we've already built unique capabilities that advance the state of quantum programming. And then there's discover the technology, which we will do now because we hop over to technology. So a tool chain from classical to quantum computation. We are developing a complete system for classical to quantum computation with quantum algorithm synthesis from classical programs to compilation and deployment on quantum processors. And then we see here an atom. The journey from classical to quantum. We are developing a toolchain to take programs written in conventional languages such as C or Python and transform them into accelerated quantum applications. This requires automated algorithm synthesis to produce a high-level description of the quantum program for a given task, paired with an optimizing compiler to produce a processor-specific executable representation. Developers can already experience some of these tools with triple alpha. And I think here is the explanation. So you start with a high-level you start with your classical program. Then here we see the refactoring, simplification, and classification, and then the quantum algorithm construction. And then, okay, there's the high-level quantum program, compilation to IR with control flow, program optimization, hardware mapping, packaging for execution on target processors, and then deployment as an API. So this is, I think, that's also written here, available in triple alpha. So these are the different stages here. So you can program in a high-level language, and then it goes all the way to a deployment as an API. And that's like the different steps that we've been talking about before, right? There's this optimization step. Then you have the hardware mapping, where it's like taking into account what the actual quantum hardware looks like, and then basically organizing the gates in such a way that they can actually be performed on the quantum computer, and adding like gates in between where they're necessary, because maybe you cannot couple this qubit and this qubit directly, so you have to go indirectly and stuff like this. Then it's packaged to an execution and deployed via API. So this looks like they are running with the cloud providers, so the hyperscalers that already have quantum computers in their cloud. Now I think it talks about the different steps here. As we don't want to stretch it for too long, I don't want to go into all of the details now. Let's quickly take a look at the algorithm synthesis part, and then the quantum compilation. We only scroll through quickly. So algorithm synthesis, bridging the gap between classical code and quantum accelerated application necessities, addressing the problem of quantum algorithm construction. To accomplish this, Horizon Quantum has been pioneering a method to automatically construct quantum algorithms from source code written in conventional languages in a way that preserves the exact function of the original program. We call this process algorithm synthesis. So classical program. The starting point for algorithm synthesis is a program expressed in a conventional programming language. This can be legacy code written in a language like C, C++, or MATLAB. I don't see Python in there though, just as a quick comment, right? But I think with these three, you can already cover quite a couple of people or quite a couple of researchers and software engineers. And no reference to quantum-specific functionalities or libraries are needed. Then refactoring, simplification, and classification. This code is then refactored. Loops and recursive function calls are broken apart into simpler and simpler elements. Once broken down to their most basic form, there is only a finite number of distinct patterns that can appear. These patterns are recognized as distinct primitives that can combine to form the complete program. And then finally comes the quantum algorithm construction. Each primitive can then be replaced by specifically designed quantum algorithms that accomplish the same task as the original primitive, but with better performance. This allows for algorithm synthesis to be applied broadly to any program. Though the level of acceleration achieved will depend on the structure of the original program. Now here I would have some questions or things that I now wonder about, because we are talking often about these QPUs, or the quantum processing unit, like for example the GPU and the CPU in your computer, and then like this broader spectrum of different compute units. Now what I'm wondering is, if you have this type of tool, will it basically take the whole program and always translate the whole thing into a quantum algorithm? Or will it actually understand which parts can be accelerated well and then only partially move this to the quantum computer, so that, like, I don't know, you have your quantum AI and you need to do some pre-processing of the data. You then want to run the AI part on the quantum processing unit, or like for your material studies, you need to do some pre-processing. Then you want to run, let's say, the material analysis part on the QPU, and then get it back to the CPU, where, like, I don't know, the post-processing can be done more efficiently. Similar to what we see, for example, with AI and GPUs and AI accelerators and things like that. And I wonder now if this compilation here is smart enough to detect those things. And maybe it's written here, but as I said, for the sake of time, I'm not going into the details here. Discover the core capabilities of triple alpha. So there's Turing complete languages, subroutines from C and C++, and code portability. We've seen that before. Okay, so there's more about how it actually works. Code, compile, quantify, and deploy applications on quantum computers. Here we see the coding part. This is what the compilation would look like. Okay, this is what the deployment will actually be. And this is now the, let's say, machine commands. And then the quantification is, I guess, like reading out and measuring the results from the quantum system. This is what we've seen already. Compiler levels and programming languages. So there's helium, hydrogen, and hardware here. Helium is currently our compiler level with the highest level of abstraction. At this level, you program in helium language, our basic like quantum programming language with familiar control structures. You can express quantum programs with loops, conditional, and subroutines. Hydrogen is a lower level of abstraction corresponding to gate level operations on an abstract quantum machine. In the hydrogen language, you can harness control flow blocks to alter quantum execution based on mid-circuit measurements and concurrent classical computation. And then hardware is the lowest level compiler level corresponding to processor-specific code. That's what we've seen above, where you like really switch, I guess, the gates. You can write programs specific to a quantum processor using its native instruction set. Here you can code in the hydrogen language or in frameworks like Bracket, I think this is Amazon, or Qiskit, and which is IBM, and deploy the resulting programs as an API. And then, okay, there's again the early access. Now there's a lot more information here, I guess. Like, I don't know, you can learn more about the code portability and so on. And if this is like an interesting topic to you, I encourage you to check those things out. We are quickly going to go here through the updates. So I'm recording this at mid of September. We see here Horizon Quantum and DMI squared sign non-binding letter of Internet for business combination. Is a highlighted post from February, but there are also more recent ones like this one from September 9th of 2025. So this is very much up to date. Okay, and then there's also a blog post here from September, why we are building a classical to quantum toolchain. And then there's some media coverage here where, like, I don't know, CNBC, for example, is covering what they are doing. Here are some information about the events. So meet us at Q2B Silicon Valley and many others. Very interesting. I mean, for sure this one is going to be interesting. Q2B Silicon Valley. Unfortunately, I cannot go. And then there's also podcasts here. Okay, so let's quickly close this by looking at the company side as well. So we've seen they have already made before some statements on the mission of the team, but now let's see what the company page says. Again, we see another one of this beautiful illustration. It says, enabling a quantum revolution. Quantum computing has the potential to transform how we tackle hard computational problems. At Horizon Quantum, we are building tools to empower developers to redefine what's possible. Who we are? Horizon Quantum is developing a new generation of programming tools to simplify and expedite the process of developing software for quantum computers. By removing the need of prior quantum computing experience to develop applications for quantum hardware, Horizon's tools will make the power of quantum computing accessible to every software developer. Why Horizon Quantum? At Horizon Quantum, we are bridging the gap between quantum hardware and software developers. We make programming tools that allow developers to work at higher levels of abstraction rather than focusing on quantum physics or hardware requirements. To achieve this, we are automating the construction of quantum algorithms from classical code and making programming a quantum computer more like conventional software engineering. Our goal is to enable developers, regardless of their quantum expertise, to harness the power of quantum computers. Then a team with science at heart. So here we see the people that are working here. So Joe Fitzsimmons is the chief executive officer. Here we see basically the C-level suite. It says at Horizon Quantum, our interdisciplinary team blends deep scientific expertise with proven leadership in the technology industry. Educated at premier institutions including Oxford, MIT, and Caltech, our core scientific leaders include our CEO, chief scientist, and principal scientist, bring decades of research experience in quantum computing and related fields. This foundation is complemented by seasoned professionals from industry giants, ensuring that Horizon's leadership is well versed in both groundbreaking research and practical application. And there we see the board as well. There's the Join Us and the Careers page, and they have offices in Dublin and in Singapore, so around the globe. With that, I'm already closing today's session. If you liked it, make sure to leave it a thumbs up. If you don't want to miss out on the next one, make sure to subscribe. You already know the story. And then see you in the next one. Bye bye.